Евгений Игоревич. Не слышит?
Я вас слышу, Галина Витальевна.
Хорошо, ладно.
Ждем
Угу.
начала.
Угу.
4 минуты.
Евгений Игоревич,
Да, да. Слышно.
кто-то будет начинать?
Вадим вообще должен быть чарменом.
Он говорил, что Чепеленкова вроде как.
Да, ну может он ее
Вероника.
попросил, я не знаю.
Давайте, может, я начну, а потом разберутся.
Давайте я позвоню сейчас ему.
Давайте я начну, а вы позвоните.
Ага.
Хорошо? Okay. Okay. Dear colleagues, good afternoon. My name is Galina Reshitova. I am from Institute of Computational Mathematics and Mathematical Geophysics, Novosibirsk, Russia. And I present our joint work with Evgeny Rominsky from Sobolev Institute of Mathematics, Novosibirsk, Russia. And the title of presentation you see on this slide. So, this is the brief content of my presentation. I start with introduction, show the system of equation, discuss the boundary condition, show numerical examples, and conclusion and roadmap. So, in the last years, the development of new technologies in industry of natural resources require new modern model of simulation and investigation process in porous media. The most widely accepted and used it is the bio model, and a lot of generalization of bio model, and but this model have some significant limitations. For example, unclear how to generalize this model for a case of multiphase media when a multiple fluid saturates the co-sample, when the medium is subject to finite deformation, or when the porosity very close to limiting case 0 or 1. So in our research, we base on modern system of hyperbolic thermodynamically compatible system for simulation seismic wave field in saturated deformous media, and this model derived from a general multiphase HTS model, which based on the same equations of continuum mechanics. So detail of this study can be found in this literature on this slide. So the governing equations of this system is the first order system written in terms of displacement velocities and deviatoric stress, and like the bio model predict three types of waves. And the structure is like the structure of dynamic elastic system, and allow us to effectively use finite differential method on staged grid like a Berrios staged grid. And our previous studies of wave field mostly was in unbounded media, and to avoid artificial reflections, we use the perfectly matched layer. But in many practical problems, it is necessary to study the field in bounded domain. So it is exists necessity to correctly introduce the boundary conditions. So the aim of this research is to numerically implement boundary conditions for the finite difference method on staged grid for this system. Let us consider the mixture of two fluids. It is the fast volume fraction 1 and 2 in deformable skeleton volume fast fraction alpha 3. And then in this case, the porosity equals the sum of two fluid fractions alpha 1 and alpha 2. And also we assume that the mass densities are constant, it means that the mixture, the mass density of the mixture present like the sum of these two elements. If we introduce the velocity displacement vector of the mixture V, and the relative velocities, two relative velocities, it is the velocities of movement of the first and second phases relative to the third phase. And if we introduce shear stresses, it is deviatoric part of the stress tensor and pressure, then we can formulate the governing equation of a HTS system. So here we see that it is the right-hand side. Phi, it is the right-hand side that help us to excite the wave field. For example, can be the plane wave or it is the point source. These two terms, alpha 1 and alpha 2, deal with the interfacial friction between two fluids and skeleton, and the last one, it is correspond to stress relaxation. So we can introduce relaxation of wave in this model. So in this equation, chi indicate the bulk modulus of three-phase mixture, and chi eta it is the phase bulk moduli of each phase. So the total stress tensor of the mixture can be computed as the difference of the shear stress and pressure, and all the components total stress tensor, shear stress and pressure can be expressed through the strain tensor via the Hooke's law. So the system one, it is a hyperbolic, and we in one-dimensional case we obtain exactly the characteristic velocity. This velocities, it is velocity of two pressure or longitudinal waves, fast and slow compressional, and one shear wave. So S1, S2, it is two compressional waves, and C3, it is a shear wave. So we see that this model, like a wave model, predict three types of waves. So to introduce boundary condition, let us introduce the most common boundary condition when on the boundary we define the normal stress. The system, as I told above, is hyperbolic, so according to the theory, the number of boundary conditions should be coincide with the number of characteristics going from the boundary into to the domain. So because I show on the previous slide has three velocities corresponding for longitudinal and shear waves, and so we need to define three boundary conditions. We define the normal and shear stress, and the third condition that there is no flow again through the normal to the boundary. So this condition can be rewritten like formulas 3 and 8, where n it is normal and sigma it is two-dimensional, it is a vector, f1 correspond to the normal direction, and the second one correspond to tangential direction. And if we admit that there is no flow in normal direction, it from the system automatically implies that the second component also vanished, and we can use this condition in our boundary when we approximate boundary condition 2. So here we write the boundary conditions on on the four boundaries, left, right, up and down. And if when we set the proper functions, we simulate certain boundary conditions. To do the numerical experiment, we use finite difference scheme on stacked grid. And like in various scheme, we the different component of the system lives in different node of the grid. So some elements lives in half node of the grid, and some components, it is pressure, shear stress, and this one lives in another grid. Okay. And here schematically we show the approximation of boundary, the elements which we use to approximate boundary conditions, and we highlight them in red. So we see it's not straight line. It is like a step. It is like this one grid. After that, we consider some numerical tests. Consider two-dimensional homogeneous poroelastic medium saturated with a mixture of water and gas in solid deformable skeleton. The properties of all phases are shown on this table. In order to do some experiment which can help us to estimate the velocity and estimate the correctness of boundary condition, we use the simplest one. We set all functions equal to 0 and only normal component equal to not 0 and equal to Gaussian pulse function with source frequency 1 megahertz. And we consider like a poroelastic media. First, we can consider, in fact, a pure elastic or poroelastic, because this model works excellent when the porosity equal to 0 for one of the phases. It means that the poroelastic media becomes pure elastic, so elastic solid or air or water. And now we consider the case where it is the wave field generated by the normal sigma from this side. And we generated to generate the plane wave that propagate from left to right. And the porosity, so it means that here it is 70% of water, no air, and elastic skeleton. So we see that appear the first fast P wave, and at the here it is the second wave, slow BR mode, and it is two different moments of time. We compare the velocity numerically and compare with the formulas we showed previously, and we obtained a very good estimation like this one and this one, this one and this one. And after that, what we do, we insert in this poroelastic media elastic circle with velocity, with this velocity, and consider two variants. When poroelastic media the same like a previous medium, it means 70%, and after that we add 10% of air. And what we see, this is the first experiment without air. And this is the second one where we add a little bit of air. And we see that if we add in the model a little bit of air, the velocity, the speed of the velocity dramatically change, and our formula agree with these numerical examples. And the next one application we want to apply this technique, it means that the solution of static parallelistic problem, if we have something boundary condition, so we need to do special code to solve this problem. But it is very nice that if we have the code that solves our dynamic system, it is very easy to adopt this code to solve exactly this static problem by introducing the relaxation terms into the equations of motion. So we take our system and just add the dissipative terms into equations of motion for velocity and relative velocities. And the convergence of to the static problem follow from the virial theorem from Landau-Lifshitz. And just a short example, we take the example of the static problem where we know exact solution, it is 1, and the boundary condition, it is from one side and another side, it is sigma, normal sigma equal to 1. And we start our process, and after some time we obtain the exact solution of the static problem. So it is a conclusion and roadmap. So we solve the HTS model for porous media saturated with a mixture of two fluid. And we use finite difference scheme and apply it for solving the correct solving this problem in bounded domain with proper boundary conditions. And the developed method can be applied to analysis of the field areas with complex structure to evaluate the effective elastic model of saturated porous medium. That is what we are planning to deal with in future, nearest future. Thank you for your attention. Questions?
Thank you, Galina Vitalyevna. Are there any questions in the room or online? There is no question? No. Okay. We can go forward. And the next speaker is Ekaterina Chekmenova with a report about preconditioner. Go ahead, Ekaterina.
It's not because of Екатерина, it's going to be the diseases of I need to share the screen. So you can see it, right?
Yes.
Nice. So yeah, I'm gonna give this and the next presentation actually, and both of them are about our attempts to solve Poisson equation, to try to do it fast and to and moreover consider applications which are important for digital rock physics, for numerical simulation of various physical processes in porous media. And one of the most well-known example of what is going on in digital rock physics and why we need to solve Poisson equation is to do numerical upscaling. So we've got our core sample, which we've got not the core sample, we've got the image of the core sample obtained by a micro CT scanner, which is really small, and we can see all the pores, not all, but all the major pores there. And our goal is to construct the media which is homogeneous but having the pretty much the same physical properties as the sample at the porous sample. So and of course we can do it. We can try to upscale various physical properties of the media, and one of the most well-known and the simplest probably case is to try to estimate the electric resistivity or thermal conductivity or diffusion coefficient of the porous material. Or to solve all these problems, we just need to solve a Poisson equation, because all these processes in static case are governed by this equation. So what we need to consider the model, which is on the left with all these pores in there. The blue are the pores, the green are the blue is the matrix, and the green are the pores. Okay, so and we assume that we need to solve a Poisson equation with a highly discontinuous coefficient sigma in there. So it may vary quite rapidly, and the amplitude of the variation may be as high as several orders of magnitude. And the goal is to construct the homogeneous model which would have the same electric conductivity at the original sample. It's one example. The other example where we need to solve Poisson equation, and we need to do it quite fast and efficient in a fast and efficient way, is the simulation of multi-phase or even single-phase fluid flow in the core sample. Again, to solve Stokes equation inside in the pore space of the sample, we need to, well, it's time evolving process, and to construct solution at each time step, we need to solve a Poisson equation to relax the pressure, and we need to do it quite a lot of time, quite a lot of number of times, because we need to do it at each time step, as I told before. So okay, that was the statement of the problem and what we do. Once we are dealing with core samples, which were obtained using the micro-CT scanners, we are dealing with the models which are already provided on a rectangular voxel-based basis. Yeah, they originally provided to us on regular rectangular grid. So we do not need to invent anything else here, and we do not. Well, even if we try to do to reconstruct the smooth interfaces between the pores and the matrix, it's not going to be the exact model, and it's not going to guarantee us closer better representation of the model than what we've got from the micro-CT scanners. So once we have a regular rectangular mesh where we know our parameters, I mean our coefficient sigma, which is like electric conductivity or thermal conductivity or whatsoever, we can construct finite difference approximation. Actually, it's a finite volume approximation with proper if we use a proper modification of coefficient modification. So the finite difference scheme looks like this, and if we are using this scheme with the proper boundary conditions, which are actually either Dirichlet or Neumann, and mainly in our case we use Neumann condition on two opposite faces, and then Dirichlet boundary condition on four other faces. So the problem is not singular, and we can solve it. And the discretized problem, well, original problem is self-adjoint, and then this discretized problem is self-adjoint, and well, this operator is negative definite, so we can apply well-known techniques to solve the system of linear algebraic equations. And of course, this technique is gonna be Krylov time method, which is conjugate gradient. But the problem here is that conjugate gradient would converge, of course. Well, if we are not talking about round of errors and stuff like this. But okay, we know that if matrix A is self-adjoint and positive definite, conjugate gradient is supposed to converge, but it's gonna be quite slow. And in our case, it's gonna depend. Well, the condition number of the system will depend on its size, will depend on the coefficient sigma, on the contrast in the coefficient sigma, and so on and so forth. And finally, we finish up with a quite slow convergence rate. And to speed up the simulations, we of course we need to apply preconditioning. And the preconditioning appears here in the conjugate gradient method. It's marked in red. So we need to construct some kind of operator B, which is in some case close to A. But this operator B is supposed to be easy to invert, or we need to be able to invert it in a fast and more or less efficient way. And in this case, we expect the conjugate gradients to speed up the. In this case, we expect the to speed up the convergence rate of the conjugate gradient method. So and okay, so and the idea, as I told, operator B is supposed to be close to A, and we need to be able to invert it, and maybe not in exact way. The idea is that operator B can be considered as a kind of a perturbation of operator A, and then we need to invert it. And when we invert it, we say, okay, what if we invert it with well, not exactly, but with some error, and but this error, we would like this error to be small enough, and thus we expect the convergence. And of course, one of the ways of doing this is to take a look at the machine learning. And the idea is the following. Okay, let us try to teach the neural network to map the right-hand sides to the original solution. Of course, it's not going to be an exact solution, but it's going to be something which is in some case close to the original solution. And we need to do it, to formalize it. And the idea is the following. We do have quite a number of images, quite a number of solutions. We apply, when we can easily apply Laplace operator to them and construct right-hand sides. So we need two sets of the data, the original the data and the action of the Laplace operator. So now we can train the neural network to map the right-hand sides to the origin to the solution. So we do not need to solve Poisson equations many times to train the neural network. We do have a priori we have exact solution and then construct the action of the Laplace operator, and that's how we construct the data set. It is very fast and efficient way to do it. We do not, once again, we do not need to solve Poisson equation to train neural network. Okay, so as I told before, what we try to do, we try to minimize the error between the original image and the result of a neural network. And this means that we minimize the norm of the error, exactly of the error of our operator. Of course, there might be another way around. If we don't want to we may not to focus on the error, but we may focus on the residual of the minimization of the residual. In this case, we do not even need the original image. We just need the set of right-hand sides. So we train the neural network to map right-hand side to something, and then we map this something back to the right-hand sides using original Laplace operator. And that's how we may try to minimize the residual, not the error. We tried both cases, and I'll show the examples what is going on there. And I should say that the results are pretty much the same, regardless to the way we decided to use. So okay, that's the example. Our original image X. Then we apply Laplace operator, getting the image in the middle, and then apply the neural network to map it back to the solution, and that's what it looks like. So as usual, when we use neural network up to eyeball norm, everything looks fine, just perfect. But it's just up to eyeball norm. Okay, what we've got here, we trained our neural network to map the residual to something. So we trained our neural network to approximate B invert. And first we applied this approach in our algorithm, and got nothing. And the first idea was, okay, when we construct the preconditional conjugate gradient, operator B should also be linear, self-adjoint, and positive definite. And our neural network satisfy neither of these three conditions, of course. And okay, we tried to put self-adjointness in our minimization process when we trained the neural network. So it wasn't that, well, it wasn't that successful. Of course, it's very hard to preserve positive to make it positive definite. So we just skip it for a while. And linearity. Of course, we also cannot guarantee the linearity, but we at least need to be sure that we preserve the norm. So if we, it means that if our original data had different norm, we need the results to be of the same norm. I mean, if we have two vectors, just copy of the one vector of the same vector, but with different amplitudes. Let's say one is constructed as the second one multiplied by 2, for instance. The result should also be just up to multiplication. We expect it. Well, that's why we changed a little bit the action of the preconditioner, and now it looks like this. So we act by the machine neural network, and then renormalize the result, just to be sure that at least we do not destroy the norm of the vector. It's not, of course, it does not guarantee any kind of linearity or anything close to that, but at least we know, we are sure about the norm of the solution. So whatever we did, I should say that we didn't succeed in constructing nice preconditioner, and the idea is the following. Okay, that's the example of what is going on. There are two 2D samples. The black represent the matrix, white represent the pores. We put different values of the coefficient in there and constructed approximated the solution, the Poisson equation, and then tried to solve it. And that's what we've got. That's how the residual looks like for different ratios of the conductivity in the matrix and in the pore space. And you see that whatever we do, our residual tends to stabilize at some prescribed level and never gets to never decay. And the problem here is that when we applied neural network to invert the operator to to construct the B inverted, we told, okay, we know that we always have an error there. We cannot avoid it. And this unavoidable error in inversion of the preconditioner leads to the problem that the conjugate gradient method never converge. It converges, but to something wrong, and this something wrong is this irreducible residual that we got. It depends on the error we push in our algorithm by using the neural network. And the problem here that if using UNet, we cannot reduce this error at all. So it's whatever we do, we can reduce it by extra 2, maybe 3%, but not more. And it means that we will always have the irreducible residual of up to like several percent maybe. So and that's our like successful experience in trying to use neural networks as preconditioners. So the only way I can see here is that increasing the accuracy of the neural network and probably using something more advanced than UNet, something like generative neural networks or something like that, because we urgently need to reduce the UNet, the neural network error to reduce the residual and to get suitable accuracy of the conjugate gradient method in general. So thanks a lot for listening to me. I'm open for questions.
Thank you, Vadim Lisica. Any questions? Yes.
Hello, Vadim, can you hear us?
Yeah.
Thank you for your presentation. I'm confused. So you are able to train well, so you eventually get the preconditioner or not? So I'm confused.
So I would rather say that we didn't get preconditioner. It doesn't work at this moment. I mean,
okay.
using UNet, we cannot
Is
do
it
anything
because of
better.
I see.
If you know like more advanced neural networks, more advanced architectures to get higher accuracy when inverting the matrix B, then we may expect a better solution of the overall problem. But at the moment, we don't have positive like experience on that.
Okay, so how about the inverse of the matrix, just kind of supervised learning kind of things, give the machine learning algorithm to train, because they have a structure, right, of the certain three-diagonal matrix, I guess.
Yeah.
And maybe
Definitely.
try to use that and try to
we need to look at the problem in more like specific details. Definitely, it's not like it was our first step. We just tried to see what would happen if we tried, and we see that if we just do it in like not very smart way, it's not gonna work.
No, it's because machine learning is everywhere, right?
Yeah.
But never works.
Okay, thank you.
Thank you.
Thank you. Go ahead again. I think.
Okay. Okay, stop. Stop sharing, share. Да, ё-моё. Так. 5. So can you see my
Yes.
slides?
Yes.
Yes.
Okay, great. So once again, let me tell you a story about Poisson solver, Poisson equation. I will definitely skip the motivation part because it's pretty much the same. It's not pretty much. It's exactly the same. So I'm skipping it and proceed just to the idea on what we were doing. And this is so I should say this is successful experience in our attempts to solve the Poisson equation. So it's more optimistic than what I showed before. Okay, so once again, we are trying to solve Poisson equation in rectangular domain. The problem is self-adjoint, positive definite, let it be positive definite. And we need to construct a good, suitable preconditioner. And once again, we are not trying to approximate matrix directly to construct the matrix B so that operator B minus 1A would be of a good condition number and stuff like this. We're not starting from this side of the problem. We are coming to it from a different side. And once again, we suggest to construct B to be close enough to A, but easy to invert. And the idea here is pretty much different. Okay, the idea here is the following. In our original problem, our operator is constructed assuming that sigma, our coefficient in our Poisson equation, to be to depends on the spatial variables, on all three spatial variables. And of course, if we assume that our sigma depends on well, our sigma is constant. In this case, the problem is very simple, and we can just get rid of this sigma 0, just divide by sigma 0 and get the Laplacian of phi, and then that's it. And then solve the problem with constant coefficients. And this problem can be easily solved using, for instance, Fourier, but not Fourier, but sine or cosine transforms depending on the boundary conditions. And then in this case, with this we can apply the spectral method, and we did it before, and we use it. We used it for a while. But now we decided to take a look at a bit more advanced technique. So what we decided to do, we decided to consider sigma 0 to be dependent on only one spatial variable. Of course, in this case, we assume that our sigma 0 is much closer to original sigma, and thus our operator is much closer to original operator, Poisson operator, Laplace operator that we are using in our that appears in our problem. And in this case, of course, we cannot. Okay. In this case, I'll show you the example of when sigma 0 is constant, but that's pretty much all the same. All the same linear algebra manipulation. So the idea is the following: if we have our sigma 0 depending only on one spatial variable, then our matrix of our system can be represented as the sum of three matrices corresponding to which approximate the derivatives along one spatial direction. And so it's our total operator is the tensor product operator, can construct as the tensor product operator. So our matrix B formally can be decomposed in the sum of these three matrices. And the good thing about it is that if we apply eigenvalue decomposition of any of these matrices, the other two are supposed to be invariant to this procedure. If we apply, so we can apply eigenvalue decomposition, 1D eigenvalue decomposition for any two of the matrices, and then get the problem. Okay, apply eigenvalue. Yeah. So the idea is that if we apply eigenvalue decomposition of any to any of these two matrices, we would get a series of 1D problems with three diagonal matrix B1. So it's originally like sorted in such a way that B1 is block diagonal with the three diagonal matrices on the diagonal, and the other ones are block diagonal matrices, but block three diagonal matrices. But anyway, we can permute the role of the spatial indices and so on. So whatever we can choose any two spatial directions to apply eigenvalue decomposition. And the thing here that if we apply this eigenvalue decomposition of matrices B2 and B3 in our case, the matrix B1 would not change. It's invariant to this decomposition. And this decomposition, as I told before, is the 1D they are 1D decomposition. So if our problem originally has 3 dimensions and 1 and 2 and then 3, and the total size of the matrix would be the multiplication of these 3 sizes, right? But if we try to apply the eigenvalue decomposition, we apply it to we need to do it for the small matrices of each matrix to be decomposed. They are of the size n2 or n3, not the multiplication of them of the sizes. So we need to apply this decomposition several times, of course, but it's small and it can be done very fast and efficient way. And of course, yeah, what we do, we use CUDA BLAS, and this can be, well, it's just extremely fast. So the idea is the following: we do it, or we did it all. Okay, yeah. When we applied all these decompositions, we can solve series of 1D problems with 3 diagonal matrix B1, and then construct the solution, and then apply the change of variables backward to construct the solution. So all this is done using GPU architecture. So and the idea here that we do not need to. So all the simulation, all the computations are applied on a single GPU. So we assign the GPU memory to store all the vectors. We construct the eigenvalue decomposition of 1D operators, B2 and B3. So if our approximated problem depends only on, for instance, B1, only on x1, yeah, direction, then B2 and B3 are just matrices with constant coefficients, and their eigenvalue decomposition can be constructed analytically, and just the matrix of the corresponding size, two small matrices of the corresponding size are stored in memory, and they can be easily stored in memory because they're really small. And then we can apply at each iteration we apply this we multiply our solution by these matrices, and we applied it using QBLAS. Then we solve 1D problem. So, and more, we got a series of 1D problem, and we organize the computations in such a way that each 1D problem is solved by one core of the GPU. So they are all solved in parallel. And then we apply inverse change of variable. So we never push the memory from CPU to GPU and back, and nothing like this. So all the variables are stored inside the GPU memory, and the solution is constructed in there. So it's extremely fast. Okay, that's how it works. So what are the good things about this approach is that it actually the convergence rate doesn't depend on the size of the problem. It means that preconditioned operator, the condition number of the preconditioned operator doesn't depend on the size of the problem, almost. So we consider the three models. These are the subsamples of the big model, which was 800 cube voxels, and then we reduced the size. And we measured the number of we considered the smallest sample, and first we studied how the number of iterations depends on the conductivity of the matrix and conductivity of the fluid filling the pore space. So matrix fluid conductivity was equal to 1. Matrix conductivity was changed from 0.1 to 10 in minus 5. So the contrast was huge, and we see that the higher the contrast, the more iterations we need, and this is pretty much expected result. So, but the point is how many iterations we need. So we, in our case, in the worst case, we need almost 900 iterations. But well, yeah, it's pretty much close to a simple multi-grid approach in this case. And the computational time, so we need to illustrate it. If when we use the desktop computer with quite old GPU, RTX 2080, it took us about 50 seconds, and when we did all the same simulations using A100, it was like less than 5. Well, it was about 5 seconds to solve this particular problem. So that's the comparison of the performance. And when after that we compared the number of iterations and the computational time if we deal with the problems of the different size, and you see that okay, why so 1000? Okay, it was yeah 200, 400 and 1000, not 800 points voxels. And we fixed the contrast of the matrix and fluid conductivity two different values, and we see that of course the number of iterations to solve the problem grows. It's not completely independent of the problem size, but it doesn't grow proportional to the size of the linear system. It grows even slower than the 1D than the size of 1D of one dimension of our cube, of our sample. So it grows really slow, and we can really consider it as almost independent on the problem size. And this is okay. Here we represent the computational time, and of course, computational time increases proportional to the size of the problem, and we see that it really increases with the size of the problem, just due to the increase of the number of operations to apply matrix vector multiplication. But still, if if we are trying to solve the problem of the size of about 1000 cube, it's gonna take us less than half an hour. So 10 to 1000 seconds is like 20 minutes or something like that. To solve extremely ill-conditioned problem with conductivity contrast equal to 10 to 4, and wow, yeah, and the problem size is about 1000 by 1000 cube voxels. So it's really big and ill-conditioned problem, and we managed to solve it quite fast and efficient. So in this case, I would rather conclude with quite an optimistic conclusions. So we managed to solve problems of the size of up to 1000 cube voxels by a single GPU for realistic complex pore space topology and high contrast coefficients. And our approach is based on the spectral decomposition of 1D Laplace operators. It's close to what is called pseudo-spectral methods, but it's used not to solve the problem, but to construct the preconditioning. Thank you for your attention.
Thank you. Are there any questions? My question is, how much faster is your algorithm than others? Have you compared?
So we didn't do direct comparison of this 3D algorithm, but in 2D, like when we were trying to understand what is going on, we compared it with multi-grid, but unfortunately, I'm not sure the details of that algorithm. I mean, how many cycles and what kind of cycles were used in there, but the minimum number of iterations which we've got in the multi-grid approach was pretty much the same as what we have.
Okay, thank you.
We didn't compare the performance, but the number of iterations.
Any questions? Okay. Thank you. And the next presenter is Dmitry Prokhorov.
Hello, do you hear me?
Yes.
And do you see my presentation?
Yes. Thank you.
Okay, let's start. I want to introduce my topic about the restoration of electrical resistivity parameters of the medium by the lateral logging sounding data. Let's start with the...
Sorry if I interrupt you. You should provide us full screen, I think.
Okay, I see full screen at my screen.
Our screen is not full screen. Can you stop sharing and try again?
Is it full screen now?
Yes, thank you.
Okay, thank you very much. Let's start with a brief introduction to the problem. The lateral logging sounding is geophysical research in boreholes based on electrical field measurements. Let us assume that we have a borehole in the layered medium. In order to obtain the resistivity properties of each layer, the researchers moves the props of the following configuration, which has a source point source of electrical current at point A, and also it has two receivers at points M and N. The prop moves along the axis of the borehole and measures the potential difference between receivers. This data forms the lateral logging sounding curve, which can be used to restore such parameters of rock porosity and saturation of some fluid like gas or oil. Also, it should be noted that the layered configuration is some approximation to a real structure, but we can assume that near the borehole we have something like parallel layers. The electric potential distribution is described by the Poisson equation, where U is the electric potential and sigma is the electrical conductivity. We use the conductivity instead of resistivity here for simplicity. Also, we assume that near the borehole, the medium has radial symmetry, so we use the Poisson equation in the cylindrical coordinates. The right-hand side here is point sources of electric current, which in our case is electrical current from props. The problem is stated in the unbounded space with the Dirichlet boundary condition at the infinity. To solve the equation, we use second order finite difference approximation, and also for averaging the conductivity at cell boundaries, we use balance method, which leads us to the harmonic mean averaging. Such finite different approximation forms the equation of system matrix, which is not symmetrical, but it can be easily symmetrized by the two diagonal matrices of the following form, where R is also, it should be noted that forward simulation for a lateral logging sounding has a lot of right-hand sides because each probe location forms different right-hand side. But the overall number of right-hand sides can be decreased because different probes can be the same location. Therefore, it can be treated as the same right-hand side. To solve the obtained equation system, we choose the direct sparse solver because the equation system matrix has only 5 non-zero diagonals. The solution scheme of direct power solvers consists of the following step: the symbolic factorization, numeric factorization, and substitution. In our problem, the usage of direct power solver has the following advantages. The first part, the symbolic factorization, is the most hardly parallelizable, but we need to perform it only once for any number of right-hand sides. Moreover, because we solve the inverse problem on the same, we solve each iteration of the inverse problem on the same grid, we need to perform symbolic factorization only once for overall solution of the inverse problem. The another advantage of direct power solvers is that there exist a lot of them which are optimized for different platforms. Because we have a lot of right-hand sides, and want to achieve high parallelization at substitution step, we choose NVIDIA QDSS library. Let's move to the statement of the inverse problem. Let's assume that M is a model space, the space of medium parameters, and the F is the forward problem operator which maps the parameters to the lateral logging Southern curves. And we want to minimize the following functional, which represents the sum of the relative errors for each probe. Also, the amount of data can be decreased by using the projection operator. For example, we can cut some part of course because the beginning and the end of the course did not represent the internal parameters of layers. Also, we can choose each 2 or 3 points of the course instead of all of them. Here we have a simple test problem. We have borehole with one layer, which parameters we should investigate. This layer is between the 2 adjacent layers. And also the borehole mud invaded some part of the layer, which changed the resistivity parameters near the borehole. So we want to investigate the resistivity inside layer, resistivity inside invasion zone, and also the radius of the invasion zone. The main difficulty of such problem is the effect which is called U equivalence. It's analytically proven that for one layer medium without adjacent layers, the different pairs of layer and invaded parameters produce equal curves, so it can be separated from each other. In the case of the presence of other layers, the other layers help us to distinguish different pairs of parameters, but not so much. Different pairs still produce very close curves to each other. To solve to minimize the functional, we use no gradient Nelder-Mead method, which is quite simple. It moves the simplex in the model parameter space by the following rules. It computes the cost of each vertex in the current assumption and try to reflect the worst point. And if reflection is good, it tries to extend it further. And if reflection fails, it finds the new point inside the simplex. Let's move to results. We apply the developed algorithm to 3 test mediums. For all mediums, the true data was obtained by ANSYS software. The first problem is a one-layer medium, and as was mentioned earlier, we want to investigate three parameters: the resistivity in layer, resistivity in the invasion, and the radius of the invasion. Unfortunately, we obtain that Nelder-Mead method can't distinguish different pairs of parameters, so we fix the radius of the invasion, and with increasing we set different radius of invasion, and for each radius we optimize the rest of the parameters. Here we can see the comparison of true data, which is blue, and 2 of the best our solutions, which is quite close to the true data. Next problem was larger, this 3-layer medium, and we want to investigate to obtain 9 parameters: 3 resistivity in layer, 3 resistivity in the invasion, and 3 invasion radius. Because we already met the problems with U equivalence, we restore these parameters in the following way. First, we choose parameters randomly to obtain the good assumption for the solution. And then, as in the 1-layer medium problem, we fix the radiuses of the invasions and restore the rest of the parameters. Here we can see the result of the results of numerical simulation for restored parameters. It's also quite close to the true data. And the last problem was the hardest. Here the data obtained by ANSYS was modified with some errors around the 10%. Here we use the same approach as the last problem, and we successfully restore the required parameters, but the error was larger, and it doesn't exceed 11% from the original data. Let's sum up the results. We developed and implement the algorithm which solves the Poisson equation in cylindrical coordinates by finite difference method and direct sparse solvers. The main advantages of our algorithm is that it highly parallel for at substitution step, and also we achieve that the matrix of the system of the equation changes at the GPU without that data transfers between CPU memory and video memory. Using this algorithm, we investigate we restore the resistivity parameters of 3 mediums, 1-layer medium, 3-layer medium, and 3 layers medium with a noise in observed data. The error of restored values of the specific electrical resistance doesn't exceed 11%, and the reconstructed radii of the invasion zones differ from the true ones by no more than 1 radius of the borehole. Thank you. That's all.
Thank you. Any question for Dmitry?
May I clarify? Dmitry, thank you for your presentation.
Thank you.
Yeah. I was wondering about this Nelder-Mean, the meat method, the simplex method.
Yes.
What was the reason for the using of that minimization? Is it the reason because you don't have the derivative function, or because usually gradient-based methods much faster, right?
Yes, you're right, but it's hard to construct the derivative of the operator. Also, in this problem, the operator isn't differentiable for radius parameters. So we prefer to use no gradient method.
No gradient. I see. Okay. Thank you.
Thank you.
Thank you. Maybe questions online? Okay. Thank you, Dmitry.
Thank you very much.
And the last presenter is Tatiana Khachkova. You are welcome.
Good day, dear colleagues. Can you see my presentation?
Yes, I can hear you and see you and your slide.
Thank you. My name is Tatiana Khachkova. I want to represent our work constructing dependence of electrical parameters on porosity and water saturation for digital models of high permeability rock samples. The work is devoted to the numerical evaluation of Archie's coefficients, specifically the cementation parameters M and the saturation exponent N, using a digital model of high permeability rock sample. As hydrocarbon reserves are typically quantified using electrical logging data, interpreted through Archie's empirical logs, accurate determination of these Archie's coefficients is critical for reservoir development and improved hydrocarbon recovery strategies. However, the conventional Archie model, where M and N is equal to 2, applies only to clean and water-wet rocks, a condition rarely met in natural reserves. To extend Archie's framework to other rocks, we need to construct two key relationships: the formation factor versus porosity and the resistivity index versus water saturation. When we constructing the first dependence, the formation factor on the porosity, we consider two digital models of high permeability sandstone. Berea sandstone model from the benchmark study presented at the bottom of the slide, under et al., and Bensheimer sandstone model obtained from the Digital Rocks portal. To validate our computational results, we employ the mentioned benchmark study that represent calculated by different methods, formation factors for digital layers and stone samples with varying segmentation approaches and porosity values, as shown in the figure 7b. The gray shaded area and solid line represent Archie's law with different segmentation factors. To construct the dependence, of the formation factor on the porosity, each model was divided into cubic subsamples with a size of 400 voxels in each direction. The Bensener model was partitioned into 3 segments along each axis, resulting in 27 subsamples, while the smaller Beria sample was divided into 2 segments along the x and y axis and 3 segments along the z axis, yielding 12 subsamples. For each full-size digital sample and all subsamples, the porosity values were calculated first, followed by the resistivity and formation factor values for each of these 3 directions. To calculate electrical parameters, we apply the algorithm for numerical simulation of electric current in rock samples that was described by Vadim Lisitsa. You can see the results. The first figure in this slide presents the calculated formation factor values for digital sample and all subsamples of Beria sandstone. In addition to the values obtained, the plot includes curves representing Archie's law for the formation factor and the porosity with the cementation parameters of 1.6, 1.8, and 2. A comparison of our calculation results for the full-size samples with the benchmarks from Andrei reveals excellent agreement between the values. The closest match is observed with the results obtained by the EUG diffusion method in the cited study. Furthermore, the first figure demonstrates that both the formation factor of the full-size sample and its subsamples fall well with the range of cementation parameters proposed by the colleague. This consistency is also evident for the Benseler sample, where all calculated values align perfectly with the same range of cementation parameters. To construct the dependencies of the formation factor on the porosity, it's necessary to solve 2 optimization problems to perform a linear regression in a logarithmic scale, based on both the generalized and classical forms of Archie law. The solid curves in this plot represent fits based on the generalized Archie's law, while the dashed curves correspond to the classical Archie's law formulation. This table provides the calculated values of the parameters alpha and m, along with the relative residue and the coefficient of determination for both approximation methods. The table reveals that when applying the generalized Archie's law, there is a stable difference in the regression coefficients. Coefficient estimates depending on the direction in which the resistivity assessment was carried out. A possible reason for such a discrepancy may be attributed to the anisotropic geometry and topological complexity of the pore space. In contrast, when applying the Archie's law in the classical formulation, the estimates of the segmentation parameters are close to each other. In addition, they are in a very good agreement with the source. The same is true for the second sample. Furthermore, in both cases, applying the generalized Archie's law often demonstrates a significant deviation of the coefficient alpha from unity, as well as reduced relative residuals and higher values of the coefficient of determination. Consequently, the usage of such form allows to significantly increase the accuracy of the approximation. Okay, when constructing the dependence of the resistivity index on the water saturation, we consider Beres-Stone model obtained from the digital rocks portal repository. Such relationship is constructed using partially water-saturated rocks models. This model sets are generated through the primary drainage simulation, where the non-wetting phase displaces the wetting phase, or inhibition simulation, where the wetting phase gradually displaces the non-wetting one, as the wetting phase fraction in the pumped mixture progressively increasing during each inhibition cycle. In this study, we first simulated primary drainage using our algorithm for the numerical simulation of two-phase flows at the core scale. First, the core is numerically fully saturated with water, and only oil is injected to displace water from the rock until irreducible water saturation is achieved. During the numerical experiment, the distribution of phases, pressure, and velocities at certain points in time is recorded. So we generate a set of models with varying water saturations. For each model, we calculated both the water saturation and the resistivity index, and then we performed inhibition simulations using 3 irreducible water saturation values, conducting 3 parallel simulation scenarios. For each scenario, at each subsequent regime, the proportion of water in the filtration flow increases. This produced distinct sets of partially saturated models for each severe cases. For each case, similar to the drainage case, we computed the K parameters, resistivity index, and water saturation for all such models. Using this dataset, we solved 2 optimization problems to construct linear regressions. Figures present the saturation index versus water saturation relationship for both drainage and inhibition cases in linear and in the logarithmic scales. The solid curves represent the trends derived from the generalized Archie law, while the dashed curves correspond to the classical Archie law's formulation with alpha equal to 1. And the table summarizes the results of approximations. The results demonstrate that when applying the generalized Archie's law, the regression coefficient for inhibition vary significantly depending on the irreducible water saturation. At the same time, using the classical Archie's law formulation gives closer values across all inhibition cases. Furthermore, this classical Archie's law estimates show excellent agreement with the laboratory measurements reported in the work Donaldson et al. This figure reproduces table 2 from this article, presenting experimental data for various sandstone samples. The measured saturation exponents range from 1 to 54 to 4, with a mean value of 3.1. Notably, our numerically derived saturation exponent for ambition 3.2 closely matches this laboratory average. In this slide, you can see the conclusion. And thank you very much for your attention.
Thank you. Are there any questions in the room or online? Okay, thank you. We have finished our workshop, I think. So thank you all for your presentation and questions. Goodbye.
That's it.
That's it.
Thank you.
Bye.
Thank you. Goodbye.
Goodbye, dear colleagues.
Sound is not working. Micro is switched off.
Mic is switched on. You can go on. Maybe the voice.
But I want to see
Yeah.
my.
Okay. One moment.
Okay.
Okay.
Okay, but I can see my slides. Okay. Can you? I use this one?
Yeah.
Okay. Okay. As I said, I think no one has heard. Okay. I will continue. Okay. So the idea is to find the feasible sequence of all jobs assigned to machines in each factory. So the idea is to perform, to obtain the scheduling plan for executing these jobs in this manufacturing system. So we want to find this sequence pi, okay? Of course, that this sequence can be seen as a concatenation of feasible subsequences for each factory, okay? To state better the situation, I'm in this slide I have again the chart. In this graph, we can see that we can see several factories. We have several factories, and then each factory has several machines. And in this illustration, we represent the jobs assigned to each machine in each factory and in each factory. And we represent also the setup times and translation times that are associated to each job. Of course, we also consider processing time. This figure illustrates, and we can see that we have a subsequence of jobs for each machine, and the objective or the goal is to obtain this sequence that we can represent by pi. Okay, so this is the idea. Of course, that most of the objectives we can have to define the criteria to solve this problem. This is, we can see that this figure represents the decision variable space, but we have to define the objective. In general, for this kind of problems, we consider objectives that are related with the computation times of the jobs, and I am illustrating for instance here the jobs, the computation times for this example. We can consider emulation times of all factors as a global objective. It is true, but the idea here is different. The idea is to model in the following way. We can consider a different objective or a different local objective, and I am using some examples here, that can be different for each factory. As an example, we can, for instance, consider that factory 1 wants to minimize the make span that corresponds to this situation here. The first one, or minimizing, for instance, the idle time of machines that correspond to minimize the average of completion times, or balance the workload of jobs in all machines that correspond to minimize the standard deviation of completion time. These are examples of local objectives that can differ from the different factories, okay? And the organization or the we can consider an organization or a complete system that can define a global objective. So based on the local objectives, the organization may define, for instance, to minimize the next span of the values of the values of T for local objectives of each factor, or the mean, or the standard deviation. So these objectives are global. The idea is to combine global with local. Okay. You have a problem? in one minute. No, I don't think.
Why can't you
Yeah,
can-
I will. Sim. É?
Is it yours?
Yeah, yeah.
microphone. Now the microphone is. Are you hearing me?
Yeah.
Yes? Okay. Let's go to the next speaker. I'm sorry for the problem that you are having. I think you are not afraid we will have you now. Now it's Clara Vaz. I think she can share your work with Clara, and she will talk about the relationship between operational, economic, and financial efficiency and user satisfaction at the health centers of prior cities. Whenever you want to, you can share your work, please. Clara, we are not hearing you. Are you? Yes, she's online. Okay, try to say something, please. Say something. Which one? We are not hearing nothing. Are you hearing us? Are you hearing me? Okay, Clara said something, I don't know what. Hello? Can you help? Share your screen, please. Huh? What is this? Clara? What is this? You are not Turkish? No. Oh. Okay, great. Huh? Where are you from?
Italy. I'm from Iran, but I come from Italy.
Okay, you are in Italy. But when I try to...
No.
No. The...
I don't know if you can hear me.
It's
The
not
sound from
working.
that computer
Ok,
is really
quem está a falar?
bad.
Quem está a falar agora? Daniel, fala. Daniel? Ok? Eu acho que é quando eu ponho aqui.
Maybe the microphone is not working.
Daniel, are you hearing? Clara? Anyone is hearing me?
Yeah.
Daniel, it seems that
Are you hearing us? Danielle?
Maybe it's better idea that Daniel start and go below. I think she's trying to share.
Clara is here. Oh.
I don't know.
I hear you now.
Do you want me to start presenting?
Yes.
I cannot hear you speak. The sound from Elsa's computer, it's very bad. It's only noise.
But we can hear you.
I don't know if you can hear me right, but I cannot hear you. Okay. Do you want me to start presenting?
Yes.
Okay.
Pode ser problema da Clara.
So, may I begin?
So, so are you hearing me now?
No.
Clara, can you present later on after?
Yes. Okay.
Okay, thank you. Daniel, go ahead.
No. Daniel? Daniel, go ahead. Present. You are sharing your screen and we can see your screen. You can start.
It's for me to start presenting, or do you wait for Clara?
Yes. Yes.
Okay, so I'll start. So, good afternoon. Thank you for attending this session. I'm pleased to present our work titled Explain Effects of Model Simplification for Generating Human-like Robot Movements in Real Tasks. The Human-like Applied Motion Planner, or HUM, is a motion planning method that generates human-like collision-free trajectories for robotic arms by solving nonlinear optimization problems. Our objective is to see how the problem formulation of these problems affects the problem resolution. So, to achieve this, an empirical test on a set of 46 nonlinear constraint optimization problems was conducted. To solve optimization problems, this is used by IPOpt, a widely used and open-source interview-based optimization solver. The performance of the motion planner in terms of computation time and quality of the solution found can be affected by IPOpt's ability to solve underlying optimization problems. On the other hand, optimization problems can be modeled using AMPL. AMPL is a preprocessing set called resolve that identifies optimization problems before solving. It removes constraints, fixes variables, and simplifies equations. These reductions decrease problem size, lower computational effort, and enable faster, more efficient problem resolution. Pre-solve has levels ranging from 0 to 10. In this where we consider 3 levels. Level 0, pre-solve is disabled. Level 1, part 1 of the pre-solve is enabled, and it assigns the bound switch variable and then tries to deduce tighter bound. At the same time, it tries to detect variables that can be fixed and constraints that can be dropped. And finally, level 10, when both parts of the pre-solve are enabled, so it executed what it's made level 1, and also several iterations of the problem are performed to do tighter bounds for the variables and linear constraints for the bounds. So, as I mentioned, the trajectory for the robotic arm is generating using global planning method called UMP. In the absence of obstacles, the trajectory consists in a direct movement, which involves moving the arm from the initial posture to the target posture. However, in the presence of obstacles, the trajectory consists in the composition of a direct movement with a back and forth movement, which guides the manipulator from the initial posture to intermediate posture called bounce posture in order to avoid collisions. As a result, the generated trajectory allows the robot to reach the target posture while avoiding obstacles in the workspace. So, for the generation of the movements, it's necessary to calculate two types of postures, target and bounce postures. The target posture can be formalized as a non-linear optimization problem that aims at minimizing the joint displacement from the initial posture to the final posture, and is subject to the following constraints. The end effector pose of the robot must fall within a specific tolerance of the desired pose, a safety distance be maintained between the points of the robotic arm and the obstacles in the scenario, and the target posture must be within the mechanical limits of the joints. The selection of bounce posture has similar constraints, but not applied to each step of a trajectory. It can be formalized as a problem that aims at minimizing the joint displacement from the initial posture to the bounce posture, and is subject to the following constraints. A safety distance must be maintained between the points of the robotic arm and the obstacles in the scenario at every step of the trajectory, and the mechanical limits of the joints are to be respected at every step of the trajectory, as well as in the bounce posture. There are three basic movements that can be planned: pick when you want to reach and grasp an object, place when you want to transport an object to a specific pose, and remove the robotic arm without manipulating an object. Pick and place movements can be divided into three stages: transport, approach, and retreat, while the move movement is composed only by the transport stage. More complex movements result from the combination of these basic movements. The transport stage consists of displacement on the joints from their initial posture to a target posture that brings the robotic's hand close to the object being manipulated. This motion results from a combination of direct and back and forth movements in order to avoid collision, so we have to compute a target and a bounce posture. The approach stage involves moving the joints from the previous posture to a target posture that enables the robot to grasp or release the object depending on the type of movement. It consists solely of a direct movement, as it is assumed that there are no obstacles near the target posture. And finally, the retreat stage that occurs after the robot grasps or releases this object during pick or place movements respectively. It also involves all direct movements under the assumption that there are no obstacles in the immediate vicinity of the target posture, so we only have to compute the target posture. Looking at the experimental setup, the beam-anthropomorphic structure Rambo was responsible to restock 5 products in a shelving unit using its right arm. The refilling process is divided into two main stages: picking the product from the support table and placing it on the shelf. As mentioned earlier, the pick and place movements are broken down into smaller stages. In the place movement, there is a slight difference. Because the shelves are inclined, the approach stage is divided into two smaller parts to ensure safe placement. First, the robot's hand moves into the shelving unit, then it places the product directly onto the shelved surface. The task begins with the robot in its own position. The robot initiates the process by grasping the first object, as you can see in the video, in this case the vinegar bottle, from the table and places. Then it goes to pick the second product, and so on. So we have 5 pick and place movements to restock the 5 products, and one movement that returns the arm back to its own position, and the task is finished. To determine the trajectory for a pick movement, it's necessary to calculate 3 target postures and 1 bounce posture. For the place movements, 4 target postures and 1 bounce posture. And for the move movement, it's necessary to calculate only 1 bounce posture, as the target posture corresponds to the home posture of the robotic arm. So to compute the entire trajectory, it has to be solved 35 target problems and 11 bounce posture problems. So the evaluation of the problems was based on the number of inequality constraints and the total CPU time required by the solver to reach a solution. We start by the dimension of the problems. This table summarizes statistics on the number of inequality constraints for each optimization problem solved, considering the pre-solved levels 0, 1, and 10. The data is defined by movement type and problem type. For the target posture problems, the number of variables remains small. Uh, Starting with the variables corresponds to 7 trajectory arms for the target posture problems, and the bounce posture problems in peak and move movements, the number of variables increases to 8. Departure is also considered. For the selection of the target posture, for both peak and place movements, the number of remains small with a pre-solve level having no impact on its number. However, when looking at the bounce posture problems are selected, the number of constraints increase significantly. For example, in peak movements at pre-solve level 0, the number of constraints ranges between 656 to 1616, increasing the pre-solve level to 1 and 10 reduces the number of constraints. This demonstrates that higher pre-solve levels can reduce inequality constraints. Also, for movement, there is a positive effect with an increased pre-solve level. A distribution of these data of the levels is represented in this figure, with actions 1 to 5 representing the peak and place movements to each product. Overall, the pre-solve process effectively reduces inequality constraints for bounce type problems, in contrasting the target problems. And we effect that the distribution remains unchanged. This is likely because the problems associated with target postures are simple in nature, so there isn't much room for simplification. So, looking to the advanced posture problems, increasing the pre-solve level in a reduction of the dimension of the problems. As it can be seen, as pre-solve level increases, the median value decreases. This reduction can be explained by the fact that the selection of the advanced posture is such that a collision-free trajectory of the arm and hand is obtained. There are constants representing each object in the robot's workspace and for each point of the robot at every step of the trajectory. As a result, the problem is more complex when compared to target posture ones. To determine if the offset decreases the number of inequality constraints with an increase in the pre-solve level and statistically significant, a cross-Coalesce test was conducted. Since the p-value is superior to 5 digits, we can say there is a significant or statistically significant effect on the pre-solve on the number of inequality constraints. Now, looking at the other side, the computational time solving to reach a solution. For each pre-solve level, each of the optimization problems were executed 30 times to ensure the reliability of the results. When plotting the computation time for different pre-solve levels, we see that in the target posture problems there is variation, the median staying almost the same across different levels, as you can see in the table. However, in the advanced posture problems, the variability is higher. The value for pre-solve equal to 10 is actually higher than for level 1, although some of the slower problems were simplified. Uh, the figure at the left illustrates the computation of the advanced posture problems for different types of movement under various levels of pre-solve. Initial 5 actions, as already said, represent the reaching and placement of product on the shelves, while action 6 represents the movement. Pre-solve has a clear impact on the computational time for bounce posture across different movement types. For example, for peak movements, pre-solve 1 reduced computation time by around 40% and by about 34% for level 10. In place movements, level 1 offers a larger reduction in the medium, while pre-solve 10 actually increased the time in relation to the previous level. Although the maximum value was reduced, the minimum value increased. For movements, which are simpler, in this case it's only one movement, overall times are lower, and pre-solve 1 still provides the best improvement, reducing time by about 30%, although in pre-solve equal to 10, it actually got worse. These results suggest that the pre-solve level significantly affects computation time for the mouse posture. To confirm this, we ran Kuskowali's tests for both peak and place movements. In both cases, the p-values are below 5%, as you can see here, so we rejected the null hypothesis that there are no difference across pre-solve levels, and they do have a statistical significant impact. To explore this difference further, pairwise Wilcoxon tests were conducted. The results shown in the table in this table indicate significant differences between both pre-solve levels for both target and boss postures. The exception is between levels 1 and 10 in the target posture for peak and place movement, where no significant difference was found. Finally, in order to gain insight into the difference between similar movements, Action 4 and Action 5 were chosen for this, as a peak movement occurs in a similar position and the place movement for these objects is to the same shelf placed next to each other. So our focus was on the difference between the bounce posture problems, as target posture had little impact from the use of pre-solve. As we can see on the table, Action 4 consists of all the equality constraints than Action 5. For example, in the peak movement in the pre-solve, Action 4 has a 1,000 constraints compared to the about 650 for Action 5. The greater number of constraints in Action 4, especially in peaking, points to a higher problem complexity, which seems to have a correspondence in the computation time in the peak movement here. Action 4 is significantly slower without pre-solve, taking over 4 times longer than Action 5. This is likely due to the starting position of the arm. Action 4 starts near the top shell, while Action 5 starts closer to the third shell, which is simpler and less complex path. As we can see, in level 1, median computation times are by about 41%, and with level 10, it further decreases. In contrast, Action 5, level 1 improves performance, while 10 actually increased computation time. In the place movement, this difference is smaller. Action 4 median times are higher, but both actions improve with resolve. Notably, Action 5 benefits more, with its median time nearly dropping 50% from level 1 to level 10. Also, we can say there are significant difference in the computation time on different pre-solve levels, as the p-value was lower than 5%. Overall, pre-solve level 1 offered the most efficient model simplifications with AMPL, as it led to significant reductions in computation time for both peak and place movements. In contrast, level 10, while reducing more constraints, didn't consistently improve performance, and in some cases, it increased computation time. This suggests that moderate pre-solve levels, like level 1, strike the best balance between constraint reduction and solver efficiency. Some of the future work could focus on developing an algorithm to determine the most efficient resolve level for a given problem. Additionally, exploring how different parameters of optimization problems, such as the initial guess, approach or retreat distance, or obstacle tolerance, affect the solving time and solution quality, could lead to a more effective parameter tuning. Some acknowledgements. This work was supported by the PT Smart Retail project, and also a sincere appreciation to research teams at MyLab of University of Minho and of the Smart Retail project. Thank you very much for your attention, and if you have any questions, be my guest. I hope you could hear me well. Oh, sorry, I forgot to turn my camera. It is question of the sound, I forgot, sorry. Thank me. Oh, okay, sorry.
Are you hearing me? Okay. So, are you seeing my screen? Mm, mm, okay. Okay. Starts. Okay. Uh, so I have to begin. So. Sorry by these technical problems. So, this is a result of the master of Elder Correia. So, he's a nurser, and he study the relationship between efficiencies of health centers and the user's satisfaction. So I will present firstly the motivation of this study in terms of and the objectives. Also, the methodology involved to use DA models and also a survey about the user satisfaction. I will present some results about the efficiency, about the user satisfaction, and finally, I present some conclusion of the study and the limitations and further research. So, in fact, the health sector, it is as a high importance in developed economies and due to its direct impact on human lives. So for the health of Cape Verde, this sector represents about almost 11% of the budget. This study basically intends to understand the current state of the primary healthcare, studying their efficiency and also their user satisfaction. And also this study involves eight health sectors in Praia City that were observed during 4 years, 2017, 2018, 2020, 2021. So basically, this study was involved 2 levels. So the efficient analysis that intends to assess 5 health sectors in Praia City. So during 4 years, a DA model was used using constant returns scale and input orientation. So this model intends to evaluate the operational efficiency of the health sectors. On the second level, we have also the ratio between the revenue and expenditure to analyze the economical and financial efficiency of these health sectors. On the second level, we study the study involves to apply a questionnaire that involved 408 users that are distributed across the health centers. So, in terms of to evaluate the operational efficiency, we use four inputs: the number of doctors, number of nurses, number of beds, number of and these are the 3 inputs, and the 3 outputs in terms of number of outpatient appointments, number of general medical appointments, and the number of nursing appointments and treatments. So these are the inputs, 3 inputs and 3 outputs that the model that the model was used. Basically, by analyzing, we use a common frontier to evaluate these 5 health sectors during these 4 years. So globally, the TC health center as the highest operational efficiency. AGT was the lowest efficiency. And also it was observed that the highest score was observed in 2017 and the lowest score in the year of the pandemic. Right? So, also in terms of operational efficiency, we analyze the mean of the inputs of the benchmarks, the units that have that are efficient, and these units have higher use on average higher number of doctors, higher number of nurses, but using less number of beds and comparing with inefficient units by providing a higher level of outputs of service to users. So basically, this can provide based on the behavior of the benchmarks, each inefficient unit can readjust their capacity in terms of beds and also manage in better way their human resources. So on the other side, we evaluate the revenue and expenditure of these 5 health centers during these 4 years, and we calculated the economic and financial efficiency, in which we observing that the TC Health Center has the highest performance in the last 2 years, and also this is the highest performance, but we have also some units, some health centers that also have a good performance, that also the revenue is higher than their expenditure, like, for example, ACA, and also PD Health Center in the last year. Problems occurs for the FZ in the last 2 years. So, on the level of the user satisfaction, we applied the questionnaire survey that involved 408 users. That basically the sample, we identified that 73% are female and with age between 20 and 59 years old, and also who come to the health center mostly due to make an appointment. The results of this survey analyze 4 dimensions of the satisfaction: the general organization, the service process, the doctors, the medical service, and the nursing service. So in terms of general organizations, we see that almost, so we are using the 5-point Likert scale, and we observe that almost all health centers obtain an average above 4. So this means that most users are satisfied with the organization. In terms of service process, by analyzing the minimum values, some users are not satisfied with the service, and also the TC Health Center has also the worst evaluation. In terms of the medical services, basically the TC also received the worst evaluation, and in terms of and the other 4 are also achieving scores higher than 3. The nursing services, in terms of nursing service, we identify that the ACA, except TC Health Center, all achieve an average above 3. This means that the users are not dissatisfied, but want some improvements. So we make the relationship, we calculate the Spearman correlation between user satisfaction and each kind of efficiency. So we identify that the operational efficiency shows a strong negative correlation with medical services and service process, but it is only statistically significant for the service process, like this. So also we observe a positive correlation between both efficiency, but is not statistically significant. And also we observe that a very strong positive relationship between the user satisfaction with the service process and the medical service, which is statistical significant. Also, in terms of conclusions, so there are eight health centers that are efficient in terms of in operational perspective. So these are benchmarks that which their best practice should be emulated by inefficient units. Also, the inefficient units can benefit of adjusting their capacity in terms of beds and also improving the staff, improving personnel staff to achieve a best service compared with the benchmarks. Also, the health centers with the worst rates must improve their policies regarding obtaining revenue and control expenses to improve their efficiency. Also, the best practice of the best ones health centers should be identified. In terms of globally, the all health centers have a reasonable and acceptable average of user satisfaction, except the TC Health Center, which has the lowest average. So we can conclude that there is still much to improve regarding user satisfaction and efficiency. And also the health centers must work more effectively to optimize their resources and at the same time providing a good quality service to users. So we have some difficulties in obtaining data from responsible institutions, also due to its reduced time availability to provide data, also in applying the questionnaire, and in achieving the answers for the users. So in terms of future research, so it could be interesting to extend this analysis for all health centers of the country, Cape Verde, and to achieve a more discriminating results in terms of efficiency. Also, it could be important to compare the several country islands to identify which is the best prepared in terms of management, organization of health centers, and user satisfaction. So, thank you.
Thank you very much. Thank you very much. I hope you are hearing us now. I am in my mobile phone just to say thank you for all. And this is the end of our session. Clara, thank you. We don't have time for questions and answers. And this is the end of the session. And thank you all for submitting papers and presenting your work. And we apologize for the conditions that we had. In the first session, I know that the screen was not shared or something happened, and the sound also you didn't hear. But we made all the efforts for everything to be all right. So thank you again, and sorry again for everything in this session. See
Okay,
you
thank
next
you.
year. Okay,
Thank
bye
you.
bye.
Okay.
E aqui, era este. Reza. Reza. This one should be selected. Here.
Isso deve ser o microfone de...
All of the
Deve
items are
daquilo, não é?
in foreign language. It's not possible. Don't worry.
Don't worry, ok. Mas eu estava a querer tentar mudar isto, experimentar isto. Não, mas nessa altura não tinha isto ligado para ver o que é que se estava a ouvir.
Olha, não vamos com bolas de borracha, já não é mal.
Não vamos porque...
E agora já não se passa lá.
Pronto, e a Irene e esse pessoal todo, para onde anda?
Aí há outros vários. Mas
Pois era uma coisa...
qual é aquela coisa do Moisés e depois?
Ah, do Maomé, da coisa do Maomé, não era?
Olha, isto é no sábado. Olha aqui as manifestações. Isto é a causa da avenida dos E4.
Okay, nice to see you.
Okay,
Bye
bye.
bye,
Thank you.
thank you.
Istambul, depois lá com a polícia, um dia depois.
Vamos seguir a extensão da vida.
Can I take the laptop?
Yeah.